Belgium is building an artificial island in the North Sea. Not a city, not a resort. A $7 billion electrical hub, 45 kilometers offshore, designed to move wind power it will never generate. It's the first structure of its kind anywhere on Earth, and it could reshape how an entire continent gets its electricity. But an island that produces nothing has to justify everything. Belgium is pushing its offshore wind capacity to the limit. In the North Sea, the Princess Elizabeth Zone is slated for 3.5 gigawatts of power across 3 development lots. If you want to follow this engineering challenge, subscribe to the channel now. As turbines move farther from shore, direct point-to-point cables become too expensive and difficult to coordinate. Continuing this approach would create a congested seabed spaghetti network of independent export lines. While the physical island represents only a small fraction of the budget, the broader transmission program is estimated to cost up to 8 billion euros. The island itself will generate zero electricity. Instead, it acts as a central collector, concentrating and redirecting power before sending it to the mainland grid. With massive simultaneous flows threatening to overwhelm the coast, Elia's transmission system must follow generation into the sea. The backbone of this offshore hub relies on 23 massive concrete blocks called caissons. Fabricated on land in Vlissingen, Netherlands, each of these hollow, gravity-based structures weighs roughly 22,000 tons. The construction consortium TM Edison, a joint venture of Jan de Nul and Deme, uses a continuous slip-forming process to pour and cure the concrete before floating the structures out. Once ready, tugs tow these apartment-sized blocks into the open sea, where they must be positioned onto a leveled, dredged seabed. Crews rely on GPS-guided systems and hydraulic controls to lower each caisson onto its foundation with millimeter precision. Neighboring units are joined together with steel plates and concrete grout to form a continuous outer wall. Sand is then pumped into the hollow chambers, providing the heavy ballast needed to anchor the entire perimeter against the shifting seabed. But the North Sea is notoriously volatile. Marine operations can only proceed during strict weather windows when wave heights remain below 2 meters and wind speeds stay under 10 meters per second. TM Edison launched the first offshore campaign in April 2025. Working through narrow windows of calm weather, crews successfully placed 17 of the 23 caissons by June 2026. If the weather holds, the consortium projects completing the primary civil works by 2027, leaving a stable 5-hectare platform ready for the massive hardware to come. The entire 5-hectare platform depends on an invisible subsea network. Power from the surrounding turbine arrays will travel through array cables to the island before being routed to Belgium's mainland grid. To survive the North Sea, these export lines require heavy protection. Specialized vessels use jet plows to bury the cables 1.2 to 1.5 meters beneath the seabed, monitoring sediment disturbance as they work. Where burial is impossible, crews install rock berms, gravel beds, and concrete mattresses. This protection is necessary because the seabed is a crowded corridor shared by fishing trawlers and commercial shipping, where dragging anchors and heavy nets pose constant threats. Strong currents, violent storms, and shifting sand waves add mechanical strain, while high voltages generate intense thermal loads. To prevent a single failure from cutting off the mainland, the system relies on parallel AC routes to provide redundancy. Operators protect this link using AIS vessel tracking, real-time fault sensors, and scheduled robotic inspections, with spare cable length stored onshore for rapid deployment. Eventually, future interconnectors may connect this hub to neighboring countries, but for now, the priority remains securing these primary lines. The proposed Nautilus link aims to connect the platform to the United Kingdom, while a second proposed link, Triton Link, points toward Denmark. Both systems remain strictly on paper, awaiting final regulatory and financial agreements. If built, electricity will flow across these borders dynamically, governed by fluctuating wind output, regional power demand, and available grid capacity. This requires sophisticated coordination. Grid operators and national regulators must manage cross-border flows through European market coupling and balancing systems, which automatically direct electricity to where prices are highest. They must also negotiate who pays for the infrastructure and how congestion is managed when transmission lines reach their limits. But expanding this network into a shared European resource escalates the security stakes. Situated in a highly trafficked marine corridor, these offshore cables and electrical installations require constant protection from anchor drag, commercial shipping, extreme weather, and potential sabotage. Because any disruption could trigger cascading outages across several countries, securing these assets is a shared international priority, keeping the physical reality of a connected North Sea grid bound to complex political and security cooperation. Constructing a massive stone and sand platform in the middle of an active marine ecosystem brings immediate ecological friction. The Environmental Impact Assessment, approved on November 21, 2024, revealed that dredging and caisson placement would disrupt benthic communities and fish populations across 12 square kilometers of seabed. Heavy machinery produces underwater noise levels reaching 190 decibels, requiring engineers to use acoustic bubble curtains and soft start procedures to protect marine mammals. Original plans featured custom nesting ledges on the outer storm walls to support declining black-legged kittiwake populations under the Life NID4 BirdLife program. However, in June 2026, developers discontinued this nesting initiative, citing ballooning costs and fears that birds would collide with maintenance vessels. Today, environmental mitigation relies on remaining measures: installing seabed artificial reef panels, laying gravel scour beds, and enforcing strict seasonal construction pauses. This 5-hectare platform will generate zero electricity. Its value relies entirely on routing and integrating power already produced by variable offshore winds. ALIA projects a 10% reduction in transmission losses and a 20% drop in curtailment. But these gains depend on completed wind farms, reliable subsea cables, and a reinforced mainland grid. The physical island itself represents only a fraction of the total budget, yet the broader transmission program has doubled to an estimated 7 to 8 billion euros, partially funded by a 650 million euro European Investment Bank loan. The Belgian regulator, CREG, estimates this could cost consumers 34 euros annually from 2034. Coordinating the civil works, electrical fit-out, cable installation, and procurement points to initial commissioning around 2030, though other frameworks indicate later milestones. Ultimately, this non-generating infrastructure cannot replace energy storage, demand management, or a fully reinforced mainland grid. It leaves open the question of whether this massive investment, the unbuilt cross-border connections, and the shifting schedule are justified. Success will be measured not by the physical island itself, but by the reliable performance of the entire transmission chain, offering a potential blueprint for a unified European power grid built not on land, but across the open sea. Transforming this isolated platform into a true European hub requires agreements that span borders, markets, and national grid operators. If those future connections fail to materialize, Princess Elizabeth Island will remain a costly, over-engineered extension of Belgium's domestic grid. But if regulators, operators, and wind developers across the North Sea successfully synchronize their systems, this platform could establish a template for offshore grid design. Similar junctions could eventually rise in deeper waters, shifting the center of Europe's power infrastructure from land to the open sea. This transition presents a stark strategic choice: a functioning, interconnected European network, or a monument to the immense difficulty of building complex electrical infrastructure in hostile marine environments. Ultimately, whether other nations copy this model depends on how reliably electricity flows through this first node, and whether the massive financial, regulatory, and environmental toll of building it can ever be fully justified. As the North Sea becomes a crowded battleground for energy, this empty platform marks a point of no return. The real test is whether a continent can successfully unite its grids across deep water. If this model works, Europe's energy future lies not on land, but at sea.